So our big focus today, I went a little more textbooky today. So I'm just going to kind of do some highlights from the textbook from chapter 13. I'm not going to go into it in great detail. Like I said, we're going to kind of talk about it. This is going to be the theoretical, the big picture idea. And then I'll really point out where I'm going to mess up to. So chapter 13 highlights. We're talking about this from an experimental design standpoint. And I feel like one of the things that have kind of been missing this semester, we've been focused on what is the business question? What is the business question? Or at least I hope that's what we've been focused on. Right? Trying to find some business conclusion. Right? What can we tell the business? How can we take the answers we have and communicate those? The analytics piece of it. But something that we do kind of need to think about is how are we getting our data? Right? So we talked about sampling. We talked about the different types of sampling. But as we're trying to do some designs, and as we're trying to do potentially some experiments, we need to think about that as well. When we're collecting our data, who are we collecting our data from? Are we doing an experiment where we're actually setting up conditions and collecting data that way? Are we doing just an observational study where we're not controlling anything, we're just observing what's happening out in nature? Okay. So there's different types of studies that we can do. Most of the stuff that we've done up to this point is just observational studies, right? The data's been out there, we've got the data, we haven't tried to manipulate anything. Okay? But it's very possible that we could do an experiment, and in your job you may be doing an experiment, and you want to actually manipulate certain conditions. I was talking with one of my students in my Saturday class, and one of the things that they work on is packaging. Right? So they'll create a package, they'll deploy it for a month, they'll try to take some results on it, they'll create a new package, they'll deploy it, they'll try and get some results and some feedback on it, and so they're creating different packages, and they're trying to test them out in different markets to see which package works the best to sell their products. So they're actually doing an experiment. And if you can think about how to set up an experiment to be able to utilize your statistical tests the best way possible, then you can potentially not have to do as many test runs. So if you can set up an experiment really well and think it all the way through, maybe you don't have to do as many test runs. Maybe it doesn't cost your company as much money to try to shut down manufacturing and change out the labels and do different things. So we're just going to kind of talk about, like I said, a high level, how can we design experiments? What are the different ways we can do things? So a couple of bits of terminology. We have a factor. So our factor is going to be a variable that our experimenter has selected to investigate. That's all it is. And we're going to have factors in our designs. And this is just what you have selected to investigate. Then we have a treatment. That treatment is going to be a level of that factor. So an example of a factor might be, I'm interested in looking at paint drying times. That was one of your first questions. And then the treatment is the different types of paint. Factor's the big thing, the treatment is the level of that factor, and the experimental units, I'm going to use that word a couple of times, are going to be objects of interest in our experiment. So what are we actually experimenting on? You can say experimental units, you can say subjects is another way to think of experimental units. Right? What are we actually collecting data from? Okay, so I use the word factor in treatment a lot. So now we have some definitions about it. Oh, okay. I didn't even know I had animations on this. How great. So analysis of variance, our big picture, right? We're using this to test 3 or more population units. This is our goal. Okay, our hypotheses are null is that all the means are equal. Alternative is that not all the population means are equal. Remember when we're talking about hypotheses, it's all about populations. So even though we're using our samples to do our calculations, when we write our null or alternative hypothesis, it's all about the population. The test statistic we're going to use is going to be an F-test. So we've had P's, we've had T's, now we're into F's. Okay, and all this does is just changes the distribution that we're looking at to be able to make some of our calculations. I'll show you a picture of the F distribution here in a second. So we do have some assumptions for the analysis of variance. So what were our assumptions for our independent t-tests? What was a big one we always checked?
Whether the population or equal variance.
Okay, so the population, the equal variances. If we're going to have an independent t-test, what do we need? You got to have independence, right? They have to be independence. Okay, so we have that here. So we have the independence. We have to have our variances are the same. And then here, our response variable has to be normally distributed. So the same three things that we were doing for independent t-tests, we're still doing for an ANOVA. This time, now we're kind of into the point where we're actually going to really be testing all of these things. Okay. I've mentioned them before, but we were focused on different pieces. Now we're going to focus on everything. Are you going to need to know this math? No. But the big picture behind this analysis of variance is we're looking for, I'm going to use this word very loosely, the between treatments estimate. So it's an analysis of variance. Right? This is the part that everybody's like, so we're doing this analysis of variance to test the difference between means. Right? So null hypotheses, are the means the same, or are the means different? But what we're actually doing the math is all about the variances. It's analysis of the variance. And so really what's happening, we're finding these variances. We're looking at the variances between our treatments. Okay, so what is the difference between our treatments? As we're looking at the variances, that also takes into account these symbols right here. We're looking at a group mean, and we're looking at a grand mean. Okay, so the means are inherently in this calculation as we're looking at the standard errors. Again, did you know the math? No, but I just kind of want to give you the big picture of how it's working. So we're looking at between the groups. Okay, what's the variability between the groups? And then we're dividing that by the variability within the groups. Okay, so for within each group, is it really spread out? Are the data really spread out? Or are the data kind of close together? Okay. So we're looking at the ratio between the variability between the groups to the variability within the groups. And that's the big picture behind this analysis of variance. Our F-test, so now instead of having a nice normal distribution that we use with our Z-test, or our T-distribution that was still looks like kind of a normal bell-shaped curve, now we have, and I couldn't make a real great picture of this, we have this F-test, this F-distribution. So it's really stacked, really far to the left, and then it kind of tails off to the right. Okay, so this is what an F-distribution looks like. And really the big thing that we're kind of looking at is we're going to reject our null hypothesis if that F-test, that F-distribution that we get, is so large that it didn't happen by random chance. Okay, so it's the same idea that we've had in the past of why when we reject our null hypothesis, the same thing happens. Now we're just, instead of using a T-distribution, we're using an F-distribution. You guys look like you're having so much fun with my theory lesson.
I guess I have a question.
Yes.
I think I'm just confused maybe on the definitions here. It's like one of the assumptions is that all the variances are equal, but then aren't we testing to see, isn't that what we're testing now?
So
Like,
the
how can that
assumption,
be,
yeah, no, I totally got it.
Okay.
So the assumption is that the variances aren't significantly different. Right? So it's not that they have to be the same, it's just that we don't want them to be very different from each other. So ideally, if the variances aren't that different from each other, and we're talking about when we're looking at the variances not being different from each other, we're looking at the within group variances.
Right.
And so if the within group variances are very different, that means they're going to be small, which means our denominator is going to be small, which means that the difference that we're going to find is really going to be coming from between the groups, not from what's messed up within the groups.
Okay.
Does that help?
I think so. And that's what we're more interested in.
And that's what we care about what's happening between the groups.
Right.
We don't want there to be a lot of variability within the groups. Because if there's a lot of variability within the groups, then that denominator gets bigger, and then we're not sure when we see that ratio, is it coming from the top, the thing that we really want there to be a difference, or from the bottom, where it's just, no, the data's just really noisy and we're really not sure what's going on. Do you have a question here?
So this is because we have like really small samples for these, right? So there has to be a really big difference for us to be thinking that they're not equal, because if we had bigger samples for all of them, they would probably get closer together. Right?
Yes. Yes. And that's going to be one of those, as our sample sizes increase, then our p-value starts to increase as well, and we start to find differences, whether differences really exist or not. So that's kind of the background of what an ANOVA is, right? So we can have an ANOVA from the mathematical perspective. Okay. We have this one-way ANOVA. We have as many groups as we want, but it's one factor, right? It's one independent variable and one dependent variable. And that's our one-way ANOVA. We could have more than one factor. We could have two factors and one dependent variable. We're going to call that a factorial ANOVA. We'll get to that a little bit later. We could have one factor, one independent variable, and multiple dependent variables. It's called a multivariate analysis of variance, a ANOVA. We could do a little controlling for some of our variables and have a thing called an ANCOVA. There's a lot of things we can do with an ANOVA. But the basis of it is what I just told you. Okay, the big picture, no matter how we do this, that F-test is we're looking at some type of difference between our groups divided by the difference within our groups. Okay, so that big foundational picture stays the same. So we can use that ANOVA, or a variation of it, as we're doing completely randomized designs, or randomized block designs, or factorial designs. So now we're not going to talk about the statistics as much as we're going to talk about the design of setting up the experiment. So a completely randomized design, an experimental design, in which treatments are randomly assigned to the experimental units. So this kind of makes sense, right? It's a completely randomized design. It really is just, as you're doing, you're just randomly assigning people. Okay, so if we had, if you were our experimental units, you are going to be randomly assigned to a treatment for my one factor, whatever it is. Okay, so let's say we have different study plans. And I've got a random generator, I'm just picking numbers out of a hat, and you're randomly assigned to group 1, and group 3, and group 2, and group 1, and group 3. That's all, and then that's all a randomized design is. You're just completely randomized into which group you're going to be in. When we see an ANOVA table, we talked about this a little bit last time, we have one independent variable, one dependent variable. So we have a treatment, this is our between, and we have the error, this is our within. So depending on the outputs of different things you'll see, those will use treatment, between, error, within. And this is kind of the look that we're going for. We talked about the relationship. I was looking at your quizzes, almost everybody got the relationships right. Almost the only time that somebody got a relationship wrong was like a typo kind of thing or a rounding error kind of thing, and I'll go back and fix those. So if that happened to you, don't worry about it. This is kind of the basic idea. And we're just going to grow this table depending on what our experimental design looks like. So an example, we could have a factor where we're looking at a type of car wax. We're trying to see, are there differences in car wax brands? The treatment would be, we have 3 different types of car wax we're looking at. Our experimental unit, we're going to try it on cars. We wouldn't want to car wax people. Our experimental unit is going to be cars, right? And then our response variable, that dependent variable, that thing we're measuring, is just the number of washes that it takes to break down the car wax. That's kind of the setup. We have our data, and when you look at a completely randomized design, you're going to have however many columns of data you want. Here's our observations, our experimental units. And then you will get an ANOVA table as a result. So looking at this, is there a difference between our car washes, our car waxes, excuse me. Yeah.
ISYS spending.
Yes, no, yes, no. Okay. Sample means. Car wax 1 has a mean of 29. Car wax 2 has a mean of 30.4. Car wax 3 has a mean of 30. Looking at those numbers, do you think there's a difference between them? No. And if we come over here, our p-value is 0.42, and if we assume an alpha level of 0.05, we're going to fail to reject our null hypothesis, which means all the means are the same. Or they're not statistically different from each other. Are you good with that? Lovely. Let's look at another one. My factor is going to be manufacturing plants. So I'm looking at manufacturing plants. My treatments, I have 3 different manufacturing plants. Buffalo, Pittsburgh, and Detroit. My experimental units are going to be managers, and my response variable is going to be the number of hours worked. So with just that little information, I can make up a scenario. Right? So I'm interested in the number of hours worked by our managers at different manufacturing plants. Okay, 5 different managers from 3 different plants. Buffalo, the mean's 55. Pittsburgh, the mean they work 68 hours a week. And Detroit, they work 57 hours a week. Do you think there's a difference between our means? Yes. Probably. Okay. And if we come over here and look at our ANOVA table, all sorts of great information, but what we really have here is, yes, indeed, there is a difference. Okay. So we reject our null hypothesis. They're not the same, so what can we conclude?
You want to work in Buffalo?
Okay, so they're not all the same. At least 2 are different. At least 2 of the manufacturing plants, the managers work different hours. Okay?
And for this to be completely randomized, you'd have had to assign a manager to like a random plant, right?
I would have randomly selected different managers.
Random, like from the plants? Would that be observational though? Because like if they're already working at the treatment, like they have to assign them randomly to the treatment.
Oh, what a great idea.
Maybe
That's
not.
such a good question. Technically, yes. Technically, you would have to have just a batch of managers and randomly assign them to the different plants and then measure and see what happens to make it truly completely randomized. So question, can you do an analysis of variance without having a completely randomized design?
I mean,
Sure, yeah, but you totally can. But for it to be a completely randomized design, then yes, you would have to randomly assign the managers, in this case, the experimental units, to a treatment. So yeah, so we would have 15 managers, and we'd just be like, hey, you're going here, and you're going here, and then let's see what happens. Very good. Alright, so we know that at least 2 of the means for how many hours they work at the different plants are different. So just by looking at these 3 numbers, which 2 do we know have to be different?
It's funny. Pittsburgh is the only one that's going to out there.
Okay, so Pittsburgh is out there. So it has to be, so Pittsburgh, it has to be different from which one?
Buffalo.
It has to be different from Buffalo. Right? So if we know 2 means are different, then the highest one and the lowest one have to be different. Okay. Now other ones may be different, but we know that the highest and the lowest have to be different. Okay. So we know that Pittsburgh has to be different than Buffalo. Pittsburgh different than Detroit? fall in it? Maybe. Probably. Detroit and Buffalo different?
No.
Probably not. Okay. But here we are just saying, yes, probably, maybe. Wouldn't it be nice if we knew? Enter multiple comparison test. So if you read your textbook, 13.3 talks about this thing called Fisher's LSD, the least significant difference. And basically what Fisher's LSD is going to do, it's going to do all the pairwise comparisons. Okay. It's going to use a T test statistic. So as you going back to the T distribution, it's like doing an independent T test. In fact, it's really, really like doing an independent T test. We looked at the independent T test formula, it looks almost identical to that. Okay. And so we're going to have some value where you can actually calculate a difference between the means. We can go find a critical value and come up with this least significant different value. So if you find the difference between these means, if it's bigger than that, if the difference is bigger, then there's a significant difference between those two groups. It's really great. ISYS has a fun little button. You click Fisher's LSD, and it'll do this for you. Last time, I didn't talk to you about Fisher's. I talked to you a thing about Tukey's. Tukey, same null and alternative hypothesis. We're still doing all the possible pairwise comparisons. The thing that's a little bit different here is we're using a different test statistic. So instead of using a T distribution, we're using this thing called a Q distribution, which is a different way to find a critical value. The idea is still the same. And we're still looking for that value, that if our means are farther than mean difference is bigger than this value, then there's a significant difference. Okay. SAS will take care of this for you too. So why Fisher's, why Tukey's? What's the difference? We're going back to our type 1 errors. Somebody remind me what a type 1 error is.
It's rejection.
Rejecting a null
Rejection.
when I wasn't supposed to. Okay? So your type 1 error is I'm rejecting the null when I wasn't supposed to. It's our alpha level. So the first thing we have is this thing called a comparison-wise type 1 error rate. It's going to indicate the level of significance associated with a single pairwise comparison. Group 1 to group 2. We'll have an alpha. Group 2 to group 3. Group 1 to group 3. Okay, comparison-wise alpha rate says that we're going to have a 0.05, the example I'm going to use right now, and a 5%, that 0.05 level, alpha level, for every comparison that I do, for every pairwise test. Okay, so let's call it comparison type 1 error rate. That's what we've been doing this whole time. Every test we do, we have a comparison type 1 error. This is what Fisher's LSD does. Okay, it's looking at the comparison-wise. We also have a type 1 error called experiment-wise or family-wise. Okay. And what it's doing is it's actually talking about the probability of making this type 1 error and at least one of all the possible combinations that we have. Okay. This is what Tukey's accounts for. So basically what Tukey's does is instead of using a 0.05, it actually does a little math and reduces your alpha level of what it's going to call significant. Okay. So Fisher's uses, if we say your alpha level is 0.05 for Fisher's, then if we have, and then I can write what? You have group 1 versus group 2, and group 1 versus group 3, and group 1 and 2 versus group 3. That's all the possible pairs we can have. This is going to have an alpha of 0.05. And this is going to have an alpha of 0.05. And this is going to have an alpha of 0.05. But for Tukey's, even though it looks like we have an alpha of 0.05, remember how we talked about the whole reason we're doing an ANOVA instead of a bunch of t-tests is so we can control for this type 1 error? Well, that's basically what Tukey's is doing on the follow-up bit. So here, we're going to have, again, 3 groups. 1 versus 2, 1 versus 3, 2 versus 3. And we'll have 1 minus 0.05. In this case, k is our number of groups, so 3 minus 1 factorial. Do you need to know this math? No. Do you need to know the big picture? Yes. Okay. In fact, there might even be a quiz question about this in your near not so distant future. A test question? No. A quiz question. That's a good quiz question. So again, you don't need to know the math. 3 minus 1 is 2, 2 factorial is... And I didn't think to do the math beforehand, sorry. Anybody want to do that in their head for me?
1097.
Look at you. Seriously? 0 what?
1097.
7. I don't like 0.097. Didn't do what I wanted to do though. Yeah, it did. So whereas here, we're looking at an alpha level of 0.05 for each individual one. Here, our total alpha level has actually been inflated to 0.0975. So we've inflated our type 1 alpha level. That's what the whole experiment-wise error rate is doing. Does that make sense? So instead of just looking at an alpha level here, an alpha level here, an alpha level here, now we're looking at, since we're doing this all together, we're doing 3 tests. What is the actual alpha level that we're looking at? So if we're okay with basically a 0.1, a 10% alpha level, that's great. But if we want to maintain a 5% alpha level, then we're actually going to have to reduce our initial alpha level. I'll let you think about this. We'll do some examples. We'll come back and think about this. A good question might be, which one of these is better? If you had to choose, and if you had to do a post hoc test, would you choose to do Fisher's LSD, where you had an alpha of 0.05 every time? Or would you choose to do Tukey's, where you looked at all of your tests at once and had an overall alpha level for it? And there may or may not be a right or wrong answer for that question. It may just be you guys thinking it through and convincing me of why you like your answer. We'll come back to this as I show some examples in SAS. So that's a completely randomized block. Our analysis of variance, a one-way analysis of variance, and then our follow-up, our post-hoc multiple comparison test. Once we get past a completely randomized design, maybe we have a little structure that we want to apply. So the next thing we have is a thing called a randomized block design. Okay? So if our experimental units are heterogeneous, okay? What does heterogeneous mean? Different. Okay? Blocking can be used to form homogeneous groups, the same, resulting in this thing called a randomized block design. Okay. So let's say that I'm interested in, I like my satisfaction scores, and my satisfaction scores on a per certain product. And my sample has people ranging from age of 10 to 80. So I have a product that applies to a lot of people. But as I'm starting to look at this, if I'm just randomly selecting people, okay, is it possible that I wind up with a group of people who have, one group has a bunch of younger people, one group has a bunch of older people, and one kind of in the middle? Can I control the ages of who gets assigned to what? Basically what I'm asking. And the answer is yes, and this is where the randomized block design comes in. So what it's basically going to do is I'm going to, you're a lot more homogeneous in age than my sample, but assume that you made up my sample, ages from 10 to 80. Okay, what I'm going to do is I'm going to rank everyone by order of age, and age is going to be my blocking variable. And then because it's randomized, okay, I'm going to have 3 different groups I'm going to put you in. You don't get to see anything. You get to see my old commercial, and you get to see my new commercial. I'm going to take the top 3 oldest people, and I'm going to randomly assign them to a group. And I'm going to take the next 3 oldest, and I'm going to assign them to a group. And the next 3, and the next 3, and the next 3. So instead of just randomly assigning anybody to a group, completely randomized design, here, I feel like age is an important thing. And I want to make sure that I have a good distribution of ages in each of my groups. So I'm going to block using age as a design. Okay? So when we do that, we wind up adding a line to our ANOVA table. We have our initial treatment and error, but now we're going to test to see, does that blocking have an effect? Does that blocking have an effect? Is it useful to block, or did it really matter? Okay. So let's do an example. So I'm interested in gasoline blends. Okay. Treatment is going to be, I've got 3 different treatments, 3 different blends that I'm going to test. My blocks, I'm going to block on automobile because I think maybe automobile makes a difference, right? So when I'm talking about the different blend of gas, a sports car versus an SUV versus a eco-friendly hybrid, they can have a difference on how the blend of gas impacts my results, right? Impacts, in this case, my miles per gallon. So here what I've done is I just looked at this, I can say it was completely randomized. Now I'm going to block, and I'm going to say, okay, I'm going to have 3 large SUVs in my group, and I'm going to randomly assign those 3 large SUVs. And then I'm going to have 3 small SUVs. I'm going to randomly assign those 3 small SUVs. A mid-sized car, a tiny car, and a hybrid. Okay. Yes?
So for each of those blocks, like we have 3 like samples within them. So like one's going to X, one's going to Y, one's going to Z, right?
Yes.
Okay.
So yeah, so I have 3. So if I have 3 large SUVs, I will randomly assign to X, Y, and Z one of those 3 cars. And then I have my hybrid, and I'm going to randomly assign my 3 hybrids to X, Y, or Z. So it's a blocking variable. We're adding an element of control. So if there's something in our design that we wish we can control for, well, as we set stuff up, let's try and control for it. Again, our results are going to come here. We just factor in the blocks, and then we still have our overall F value. We interpret it the same way. So is there a difference between our blends?
It's 0.05.
No. Depends on my alpha level. So if my alpha level is 0.05, is there a difference between my blends? 0.07 p-value greater than 0.05, we fail to reject our null hypothesis, and we say that all the blends have not significantly different means. Yes?
So the automobiles for the blocks, are they also the experimental units?
In this case, yes.
Okay.
Yeah.
Could those be different though?
They could be different. Right, so I could block on age, but my experimental unit would be the person. Yeah. So in this case, it just happens to be both the block and the experimental unit. So the idea of a randomized block design. It went from completely randomized, now we have a little thing that we can kind of block on, that we can control for. The next thing we have is a factorial design. Keep taking it up a notch. For the factorial design, we're looking at conditions with 2 or more factors. Okay, so now we're leaving the realm of, so here, we had, or so for our completely randomized design, we have 1 independent variable. For our randomized block design, we still just have 1 independent variable, 1 factor. Now we're going into factorial design, and now we have 2 factors, or 2 independent variables. Okay. The term factorial is used because our experimental conditions include all possible combinations of the factors. Okay. So we're going to look at factor A, we're going to look at factor B, and we're also interested in the interaction between factor A and factor B. And so this is kind of the question of why, so we started out with like, why do t-tests? Right? So why do an ANOVA when we can just do multiple t-tests? Going on to a factorial design, the question is why not do 2 one-way ANOVAs? Why go and do a factorial ANOVA? Okay. And the answer here is the interaction piece. Okay. So we can look at the difference between one factor and a one-way ANOVA. We can look at the difference between the other factor and a one-way ANOVA. But are we missing an interaction? And that's where our factorial ANOVA comes in. So again, we're going to make our table a little bit bigger. Okay? So the things we're going to look at, we've got factor A, factor B, and our interaction. We're keeping that error piece the same. Okay, in this table, we're going to wind up having a p-value for factor A, a p-value for factor B, and a p-value for the interaction. So that means we're going to have hypothesis tests for the factor A, for factor B, and for the interaction. So here's a factorial design. So in this case, we're interested in the industry type and the location of the industry. Okay, so now I have 2 factors. So I could have done a one-way ANOVA where I just did industry type. And I could have done a one-way ANOVA where I just looked at location. But we're interested to see, is there an interaction? Okay. So our response variable is going to be hourly wages. We don't have our experimental unit in here, but I'm assuming it's going to be workers. So factor A, we're going to have our industry type, and it's going to have type 1 and type 2. Factor B is location, and it's going to have a treatment of Cincinnati, Cleveland, and Columbus. So now our data are set up in such a way that this is industry. This is, so I guess we should really look at it. So factor A, factor B, let's write this so you can see it later. Factor A, factor B, and then here is your actual response variable. Okay, so this could turn out to be a whole bunch of values, or it could turn out to be just an average value. Okay. Let's see if I have. Oh, I didn't come up with a new comment. Alright, so hypotheses that we're going to test. And I don't have this written out on this slide. I have it on my other one. we're going to test the null hypothesis will be no factor A effect. Then we'll have another null hypothesis that is no factor B effect. And then we have a null hypothesis that says there's no interaction. We're actually going to start here. First thing we want to do, and I'm going to leave you guys at kind of a high level with this factorial number, okay? So the first thing we're going to do is we're going to start with no interaction. So we go down to the interaction row. We find our p-value, and our p-value is 0.25. So assuming an alpha level of 0.05, we reject or fail to reject our null hypothesis. Fail to reject. Okay. Our p-value is bigger than our alpha level. We fail to reject, so there is no interaction.
Can you explain what you mean by interaction?
Absolutely. Can I hold on for a second on that? Because I have a picture in my later slides that actually illustrates it really well. Basically what an interaction is so maybe industry 1 is higher in Cincinnati, industry 2 is higher in Cleveland, and industry 3 is higher in Columbus. So there's not a straight, like, oh yes, industry 1 is always higher, or industry 2 is always higher. There's some type of interaction that when you put these two things together, different things happen with the needs, right? So if I was trying to say, is there a difference in just location? Well, maybe there is a difference in location, but if I add, is there a difference in industry? Maybe there is. But what I'm really interested in is there a difference in interaction, or in industry and location? And if they're different for different places, then that's where the interaction comes in. So I'll show you a graph here in a second that clears this up a little bit. Okay. But really it's just, the whole idea is, I could have done a one-way ANOVA for the factor A. I could have done a one-way ANOVA for factor B. But instead, is there something happening that we're not seeing? That's what the interaction piece is. Okay? Yes.
If any one of these numbers in the table was something like 6,
Yes.
then we'll surely have an interaction.
Most likely, yeah. Yeah. So if there was something really small that was kind of thrown out of whack,
Irrespective of anywhere in the table, it will have an interaction.
Most likely. So in this case, there's no interaction. And if there's no interaction, then we're good to go. Okay, so if there's no interaction, then we can go on, we can check A and B, and we can be comfortable in the answers we get there. Okay. If there is an interaction, then you're going to stop. Okay. If you go on and take experimental design, you're going to learn all about main effects and some other things. You'll start going into deeper dive into figuring out what happens here. We're going to say if there's an interaction, we're going to stop, and we're going to go look at the descriptive statistics, and we're going to talk about things that way. Okay. Again, this is a bonus piece on your assignment. You're not going to be tested on doing this, but if you want to, I want you to have that ability. We're just not going to get into it really far. The big thing I want to focus on for you guys is just the idea of that one-way ANOVA, and then the fact that you can extend it to different scenarios. So in this case, we don't have an interaction, so we can be comfortable with our factor A and factor B. And can we say, is there a difference in factor A, so in industry?
5%.
Assuming at a 0.05.
Factor A.
In factor A, no. Right. So in factor A, there is no effect. We already said there was no interaction. But in factor B, in this case, that's going to be our location. Is there an interact, or is there an effect? Yes. So here, it's not so much the industry, it's the location that has an impact on our locations.